Okay, folks, this is, we're still on section 5-2. This is recording number 5, hopefully their last recording. Okay, so the next section here is talking about expectation. And it's this concept that what do you expect? What do you think is going to happen? Now, obviously, we don't know, but what is your best guess? That's how I think about the expected value. So the author talks about some applications here, and one of the applications he mentions is insurance. So the way it would be used in insurance, for example, would be somebody comes and wants to buy an insurance policy and they're 20 years old. Well, you expect them to live until they're, let's say, 85. So that determines how much of a premium they have to pay. On the other hand, somebody comes and wants to buy insurance and they're 70. Well, you expect that person maybe to only live till to age 75 or whatever age the expected longevity is. So those are the kinds of examples that you would use it in business. And as you can see, it's very important. And now nobody knows how long somebody is going to live. However, for purposes of determining how much of a premium they're going to pay, it's very important to have your best guess. Let's take another example from insurance. How many accidents do you think a 16-year-old is going to have? What's your expected value for the number of accidents as compared to the expected value for somebody that is 60 years old that's been driving for 50 years or 40 years or whatever? Okay, so expected value is used in a variety of contexts. Another context that it's used in, and I'm not going to talk about it because it just gets too complicated, but one of my many things that I'm studying online is physics, and let me take you down that path just for a second here, something you may have heard about. Let me stop the recording for a second. Okay, perhaps you've heard of quantum mechanics. That's the physics of the very, very, very small. Okay, in quantum mechanics, we're talking about very, very small items and quantum objects. Let's take a look here. The quantum mechanics is a fundamental theory in physics describing the properties of nature. That's kind of generic. Let's see if we can come up with a better definition here. Bear with me. Okay. See, this is why we use such prosaic or mundane examples. When you try to start getting into some of these other uses, it's awfully difficult. Okay. I guess what I would try to say is that quantum mechanics deals with, what are the fundamental particles in nature. Electrons are examples of what are called leptons. We also have hadrons, which are composed. Hadrons are subatomic particles that are composed of what are called quarks. Quarks and leptons are expected or believed to be the fundamental particles in nature right at this moment. And of course, things change as we go along, get more theory going. Okay, so in quantum mechanics, we have this concept of things are not necessarily what they appear to be. All you can do is measure an electron. You don't know exactly where it is. You can measure it, but where is it before you measure it? Nobody knows. There's a probability there's a probability associated with the electron. Is the electron a wave or is it a particle? These are all fundamental questions, and they all deal with probability and statistics. So what I'm telling you is this class is going to be of great value to you if you go down the road into any sort of physics or engineering. So in any event, we use expectation value in quantum mechanics, quantum physics. And what is it? The expectation value is the probabilistic expected value of the result or the measurement of an experiment. It is, in a sense, it's an average of all of the possible outcomes of a measurement, and they're weighted. It's a weighted average. It's weighted by their likelihood, by their probability, exactly what we're talking about. Now, it's not necessarily the most probable value of a measurement because the expectation value can have a zero probability of occurring, okay? All right, so for example, something that can only yield integer values, it can have a non-integer mean, all right? but it's a fundamental concept that we use all the time in physics. Okay, so I just wanted to mention this to you because I wanted you to see that, these stupid examples that we use in this book, the reason we use these examples is because it's something we can all understand without getting too far in the weeds of other topics. Okay, so what do we mean by a expected value? The expected value of a discrete random variable of a probability distribution is this theoretical average of the variable. It's exactly the same formula that we had before for the mu. So mu is the expected value, which is summation of all these guys. You take all of these random variables, all the possible outcomes, you weight them. When I say weight, that's W-E-I-G-H-T-E-D. You weight them by the probability and add them all up. That gives you the expected value. Okay. All right, so that's what he says here. It's the same as the formula for the theoretical mean. Okay, so here's an example. Now, this is one that we can all understand. We don't have to get into this quantum mechanics stuff. 1,000 tickets are sold, $1 each. What is the expected value of the gain if you purchase one ticket? So this could be a lottery ticket. This could be a ticket for Little League. Everybody's chipping in some money. They're going to win a TV, but they sell a lot of tickets, make money for the kids. Okay, so they sell 1,000 tickets for $100 each. So that's $1,000 they get. They use 750 of that to buy the TV. So what's the expected value of the gain if you buy one ticket? Okay, so you either win or you lose. So that's the gain. That's your X. Okay, the probability of winning or losing. Well, the probability of winning is 1 over 1,000. One ticket out of 1,000 tickets. The probability of losing is 999 over 1,000 because that's how many tickets aren't going to win. Okay, so for a win, the net gain is only $7.49 because you paid $1. Okay, you don't get the dollar back for the ticket. For the loss, it's going to be -1. That's how much you lost. You cost you $1. Okay, so use the formula. Probability of 749 is 1 over 1,000 plus this probability here, 999 times the -1. All we're doing is we're using the exact same formula that we used before. So on average, you're going to lose 25 cents on each ticket purchased. So the reason I'm belaboring this example is this is an example I think that illustrates sometimes how foolish some of these concepts can be. I mean, when you buy the ticket, in our normal way of thinking, the ticket is worth nothing unless you win. If you win, you got a TV. Hey, that's great. If you don't win, you got nothing. So you don't talk about on average losing 25 cents. But this is something that can be, this concept can be utilized in other contexts where it does make more sense, okay? The author talks about this right here. He says, the expectation is negative 25 cents. Well, you don't lose 25 cents, okay? You either win it or you don't win it, okay? What the expectation means is that on the average, the loss is 25 cents or 0.25, 25 cents for each of the 1,000 ticket holders, okay? I'll let you read that sentence yourself. Okay. All right. So I think this is pretty clear here. Okay. So here's another example. Example 513, talking about Uno cards. The variable that we're dealing with here, you can show a 0, you can show a 2, you can show a 4, and so forth. Okay. Find the expected value of the card. All right. So it's the same exact thing that we've been doing up until now. It's worth doing just to make sure you know how to figure out how to calculate the mean, how to calculate the expected value. Okay. So here's another one talking about in financial context. Okay. We're talking about bonds here. We have two different bonds, bond X and bond Y. We want to talk about the expected value. Now, again, this is something we can wrap our arms around, but I swear to you, there are other examples that are a lot more interesting that have the same basic concept. So bond X pays a return of 4%, but it has a default rate of 2%. So those are probabilities, right? 4%, 2%, those are probabilities. Bond Y has something different, okay? So find the expected rate of return and decide which bond would be a better investment. Okay, and the key is that it's all or nothing. When the bond defaults, you lose everything. You don't get it. You don't get a portion of it, according to this problem. Okay, so the first one, the return is 4%. That's just the interest rate. 4% times $5,000. That's $200. Okay, now the expected return. What do we expect? What's the average return? Well, it's $200, and there's a 98% chance of that happening. Now, where does that 98% chance of getting that comes from? Well, bond X pays a return of 4%, and it has a default rate of 2%. So if it has a default rate of 2%, that means that 98% of the time everything's cool, everything works, right? So that's the 98% times the 200. Okay. On the other hand, it has a default rate of 2%, and when you have the 2%, it's a negative 5,000 because when you lose the $5,000 that you invested here, you invested $5,000. When you lose it, you lose it. You lose the whole thing. Okay. So the expected value, that's the mu. So it's a probability of getting 200. So that's random variable number one is $200. The random variable number two, the x sub 2, is negative $5,000. The associated probabilities are 98% and 2%. So 98% times x sub 1 plus 2% times x sub 2, which is x sub 2 is a negative number. When you do the calculation, you come up with $96. You do the exact same thing for the second bond, and you come up with $73. Okay, so this is a better investment, even though let's see if there's any counterintuitive aspects to this. Give me a second. So yeah, what they're saying is bond X is better, but you would not know that if you couldn't do arithmetic. Or you couldn't do statistics, you would not know that. This is an example of what I said before, that you can't really be a critical thinker unless you can do mathematics. You look at this, bond X pays 4%. It has a default rate of 2%. So you might look at that and you might say, oh my goodness, that's a bad investment. 2% of the time it defaults. Bond Y pays a little bit less, but gosh, the default rate is so low on that one. It's only 1%. It's half of what is half the risk. Okay, so that's probably a better investment. Well, you don't know. I mean, you have no way of knowing unless you know how to do the statistics and the probability. So once you do the calculation, then mathematically speaking, the first guy, the bond X, is the better investment. And you can't do that just by looking at it. You have to do the mathematics. Okay, so we got all these other examples here talking about gambling. I'll let you take a look at that. This is talking about radiation exposure, okay, at 3 Mile Island. Very, very apt, very important, okay. Using current events, if we were talking about the coronavirus, you could have the same exact basic concepts would be in play here. So I urge you to read this. And you can see page 309 for the answers. It's just kind of an interesting mental experiment, if nothing else. Okay, so that's the end of section 5.2. As always, I urge you to take a look at the exercises, not to do them all. I mean, I know you can't do all of these exercises, but try to find one or two that are really interesting to you so that you can use that as your standard example that makes sense to you. Trust me on this, it will help you understand the material if you do that. Okay, so this is the last recording for section 5.2. This is recording number 5.